So my talk is Learning Empathy from Pokémon Blue. My name is Tess Griffin. I am a developer at Thoughtbot. Now, let's talk about Pokemon. The first Pokemon game was made by a small team for Japanese audiences. The game was made on a very small budget, and the programming team was only 4 people. In 1996, Pokemon Red and Green were released, and sales vastly exceeded expectations. Later that year, an updated version was released in Japan with improved graphics and more polish. After it was clear this game was far more popular than anybody expected, there was a mad rush to localize it for Japanese audiences. 2 years later, in 1998, Pokemon Red and Blue were released to the rest of the world and would go on to be actually the highest grossing media franchise of all time. Yes, higher than Mickey Mouse, Star Wars. It's actually like top of the list, if you can believe it. Even if you've never played Pokemon, I wager you've seen this one before. This is Pikachu, by far the most famous Pokemon, but there's actually a close second. This horrendous sprite is Missingno. You could only encounter this Pokemon through a glitch. But almost everyone knew about this glitch. One of the things I find most interesting was how widespread this glitch was. I ran a small survey, and 80% of people who owned the game knew about the glitch. And 80% of those people heard about it through word of mouth, not the internet. And there was a good reason. Missingno could duplicate items. So word spread far and wide about how if you ran out into this glitched Pokemon, it'd duplicate items for you. This glitch had a lot of names. The old man glitch, the item dupe glitch, the rare candy glitch, lots of names. So let's take a look at how you perform the glitch. So we start off in Viridian City. This is an early area of the game, and this old man gives us a tutorial on how to catch Pokemon. The battle starts, the old man shows us how to catch a Weedle. Thanks, old man. Now, we'll open up the Pokemon menu, and in the original games, you could only travel by flying. Our sprite turns into a bird, and we fly to Cinnabar Island. We go to the East Coast. I'm going to open up our item inventory, go down to the 6th item, and see we have 1 rare candy. Then I am going to get Squirtle, and we're going to surf up along the East Coast. Eventually, while surfing, we get an encounter with a wild Pokemon. This is what an encounter looks like in the game. There's some battle music that I forgot to record, but this is Missingno. You see it's level 146. We send out our Pidgeot, and we're gonna run away because we actually would quickly lose the battle. Open back up our item inventory, and now we have 129 rare candies. This is just the character that I guess responds to 12 in the text encoding. So if you've never seen this glitch before, this probably seems like an extremely random sequence of events for such a specific outcome. And it is, and let's break down each piece of this. As with most major glitches, there's no single bug that's responsible here. This happens because of a bunch of different bugs. And in most cases, you can't even really call them bugs, just properties of the code being used in unexpected ways. And I want to say up front, I did not work on this game, nor I've interviewed the programmers who did, but I think we can infer a lot about what was intended in the code and the constraints that they worked under. But I want to make it clear that a lot of this is speculation. Now, with that out of the way, let's start going through each of the pieces. So the first question might be, why do we go to that coast tile? So this is what a tile that the player's character occupies looks like on water. It's kind of a seal, I guess. The game works on a grid system, so the player can go left, right, up, or down in one tile. So when we remove the player, this is what it looks like. It's actually made up of 4 subtiles. So the top left is 8-8, and the bottom right is 9-9. And to find out why this coast tile is special, we're going to take a look at the Ruby version of the code that checks for if the player runs into a wild Pokemon. Now, obviously, the Game Boy game was not written in Ruby. It was written in assembly, but I've translated the code to Ruby for ease of reading. So first, we're going to load, yeah, you're welcome. First, we're gonna load up the bottom right tile where the player is standing on and assign it to tile. And then we need to calculate the encounter rate. This is the percentage chance that we have to run into a Pokemon with each step. So if it's a grass tile, we're going to grab the grass encounter rate for the current area. And then if it's water, we grab the water encounter rate. Otherwise, we exit out because the player can't encounter a Pokemon in that area. Then we'll do some math to determine if a wild encounter occurs. And I've commented that out because that part isn't relevant. Then we're going to load up the tile again, but this time it's the bottom left subtile instead of the bottom right. And then we check again to see if it's water. If it is, we pick a random water Pokemon. Otherwise, we'll pick a grass Pokemon. Now, this bug stands out pretty clearly here. We're loading tile twice, and when we're determining if an encounter can happen, we're looking at the bottom right, but when determining what type of Pokemon, we look at the bottom left. Now, as we're going up and down this coast, the game is continually doing these calculations, thinking that we can encounter a Pokemon because of the water. But when we get an encounter, we get a Pokemon from the grass encounter table because of the land there on the left. Now, you can see here the bug stands out because I translated it to Ruby. But the thing is, Ruby isn't assembly, and we lose a bit of important context when we translate the code. The bug stands out in the Ruby code in part because I can show you these two on the same screen. They're relatively close together. In the assembly, this commented out part is actually about 50 lines of code. So you wouldn't see them at the same time. And that detail alone is a reason I could see this slipping through any kind of code review that they had. And then there's another important piece of context. In Ruby, you wouldn't assign tile twice. We've already assigned it up on top. Why would we need to assign it again? In Ruby, we can have however many variables we want. The VM just handles where those get stored for us. But in assembly, it doesn't quite work like that. In assembly, things get stored either on the stack or in a register. They could put things on the stack, but their stack was only 207 bytes, which is incredibly tiny. So they only ever used it when they absolutely needed to. So in Ruby, you'd reach for just local variable, but in assembly, you would store it on a register. And a register is sort of like a global mutable variable for your CPU. You have a very limited number of them. And for the Z80 assembly, there are only 4 registers that were 100% general purpose, where you could use them for anything. So could you write your whole program with only 4 global variables and not introduce bugs like this? I don't think I could. Okay, so we can encounter grass Pokemon when we're on water tiles. But how did players use this to duplicate items? We need to pair this with something else. So let's look at the code that happens when you enter a new area. So in the previous slides, we had the current area, and that gets modified a few times. So whenever we switch areas, we're going to a global section of memory where all of the grass encounter tables are stored. This is like grass encounter. This is the list of the percentage chance that you have to run into a grass Pokemon and all of the different kinds you can run into. So we're going to grab the rate for the area with our current area ID. And then we're going to check to see if it's greater than 0. If it is, we copy over the whole table to the current area's grass encounter table. Otherwise, we exit out. Whatever's stored there before will continue to be stored there. In other words, we can keep old grass encounters from other areas. So this is why we travel to that island. When we use fly, we can only travel in between towns. And Cinnabar Island is a town, but it has water that we can get to without passing through a different grass area. And so we keep the old encounter table because of that. So because of that, we can encounter Pokemon that normally wouldn't appear in that area. So people would use this in other ways to like encounter Safari Zone Pokemon that wouldn't normally appear outside of that area. But we, in this example, want to duplicate items. So in order to duplicate items, we need a grass encounter table that isn't a real one. So to understand what all this means, let's look more concretely about how these tables are represented in memory. So the current grass encounter table that the player was in was stored at this memory address, D887. Everything on the Game Boy had very specific memory addresses. And this is the memory address for the grass encounters table. So the first byte was the rate, and then the lower the number, the more likely the player was to run into a wild Pokemon. Then we had 20 bytes, which were a series of pairs. So the first byte was the level, you can see it there on the left, and then the right was the actual ID of the Pokemon, and then each different slot is a different percentage chance. So you can see like the first one, there's like 19, about 20% chance to run into that specific Pokemon. So this is an example of a grass encounter table for a real zone. So at memory address CFA3, this is the grass encounter table for Mount Moon. So Mount Moon, if you're not familiar, is a notorious part of the original games. It's a series of long caves that are like hard to navigate through. And so first we're gonna translate the IDs. So 6B corresponds with Zubat. And then, so we'll translate each of those to their corresponding Pokemon. This is the first part of the finished table. As you can see here, we have like a 60% chance to run into Zubat. And the whole table is like, well, it's all Zubat. If you've ever played the games, like this is the experience of just like, it's all Zubat. Like I was a kid and just would have like nightmares about running into Zubats. And it's really cool to see that like represented like in the table, in the code. So this is a real grass encounter table. Now we're gonna create a fake grass encounter table. And we'll actually go back to the tutorial from the old man. The glitch was called the old man glitch because, well, you can see his beautiful name is old man. So what's important to this glitch is that he has a name. Everything about Pokemon was optimized for code size above all else. They needed their code to occupy as little space as possible to fit into the smaller cartridge. If your code was too big, you would actually need to, the next size up was double the amount of ROM in the cartridge, and that was just too expensive. When Pokemon was originally being written, they just didn't have the budget to do that. If you're writing this today, you might have a dedicated piece of code for your tutorial, but if you're optimizing for code size, you could simply just put conditionals around the regular battle code. So this means that this tutorial is just a normal battle. But instead of the player name, old man gets put where the player name would be. So we need a place to temporarily store the player's name. And where would they do that? The grass encounters table, actually. For this example, my character's name was 6 uppercase S's, like, so this is the memory address for that. And so let's store that on the current area's grass encounter table. It just so happens, coincidentally, that capital S corresponds to 80, which is, well, it corresponds to 146, which is the ID for a Missingno. And this is the copied over grass encounter table when we store my player's name. So you can see here we have a very high percentage chance to run into that level 146 Missingno. Those bottom two are called Tick M, and they're kind of like Missingno's glitch counter, like glitch sister. We'll get into more of that later. So what is Missingno? Contrary to what you might think, it's not actually a single Pokemon. There are actually 39 distinct Missingnos. And it's not just reading like garbage data. So the sprite is clearly like garbage data, but it has a well-defined name, Missingno, and it has lots of other like well-defined attributes. So why are some of its attributes garbage and some not? So we'll see how Pokemon are actually stored in the code. When most people think of a list of Pokemon, they think of the order that they appear in the game, in the Pokedex, the in-game encyclopedia. So each Pokemon has a number associated with it, and they're loosely ordered in the order you would find them in the game. But that's not how they're stored in the code. So Rhydon is actually the Pokemon with the internal ID of 1. In the code, most of the data related to Pokemon are stored in the order that they were created. The game originally had 190 Pokemon, but it shipped with 151. So Missingno is what's stored in the slots where they cut out Pokemon that weren't released. So for the most part, these entries for Missingno were just zeroed out. They weren't deleted, they were just zeroed out, with exceptions like its name. That's why its name is Missingno. So for anything ordered by the internal ID, we get well-defined, but it's zeroed out data. Anything stored in the Pokedex order, we get garbage data. So we'll take a look at the code for grabbing the data for a Pokemon. So it's this Mon data, which is the Pokemon's base stat table. This is stored in Pokedex order. This also includes a pointer to the sprite. So first, the game looks up what a Pokemon's Pokedex number is from its internal ID. The internal ID for Missingno is 0. So we need to convert that from the Pokedex ID to an actual index in an array. Since the Pokedex starts at 1, we need to subtract 1 from that. Now in Ruby, this would just give us -1 because we don't have concrete integer types. But in assembly, this is a 1 byte unsigned integer, which means that when you subtract from it, it underflows to 255. So we're actually indexing the next array at 256. So in Ruby, this would just give us nil when we're trying to index on a part that doesn't exist. But in assembly, the array we're indexing into only has 151 items in it. So we read way past the end of the array. And so that's why the sprite is garbage data, because it's trying, the decompression algorithm for the sprite is actually reading the data from like some trainer's Pokemon on level 17. It's like it's trying to decompress what it thinks is a sprite, but it's actually just code. So that's why it looks like just complete garbage, because it's actually like, oh, this code is a sprite. It's actually code. That's why it looks so weird. So most data isn't stored in this Pokedex order, so we actually mostly get valid data. This is a screenshot from the Japanese version of a Pokedex entry. It's just like information about the Pokemon. So it's actually the question mark Pokemon. This is what happens if you actually capture a Missingno. And it has a placeholder like height and weight, and the comment translates to comment to be written. So it actually, if you catch it, it actually has valid data, which is super interesting. And some Missingnos actually have like more unique data. So the sprite for like these fossilized Pokemon are actually like Missingno, which is pretty cool. So which versions of Missingno you saw were based on your name, because you would store the player's name in the grass encounter table. So that's why everybody could encounter different versions of Missingno. So, but if it was based on your name, why could everyone perform this glitch? And that's because there was actually a control character at the end of your name was stored as 80 in decimal, which just happens to be an ID of Missingno. So if your name was an even number of characters, you could always encounter Missingno. Every built-in name had the right number of characters. So these are screenshots for the default names. A lot of players didn't even pick their own name. They just use one of like the preset ones for you. And by pure luck, every one of these has the right characters to encounter Missingno. And They were also like common in like the English language. So uppercase S, H, and M, most lowercase vowels were all mapped to Missingno. And even then there was actually a catch-all if your name didn't fit into any of those. Every custom name could at least encounter a tick M because like I think it was like it mapped to 0 and there was always 0. And so we call it tick M because that's the only characters that aren't just garbage. So unlike Missingno, tick M is actually all garbage data. So you actually don't want to catch tick M because that will kind of mess up your game. But actually catching regular Missingno is fine because it's just zeroed out data, not just garbage data. But actually encountering tick M will still duplicate your items, which is why everyone could duplicate items. So now let's talk about why it's specifically the 6th item in your inventory that gets duplicated. That has to do with when you encounter a Pokemon. So this is the Pokedex. Its function in the game is to keep track of every Pokemon you've seen or caught. So if the name appears, that means you've encountered it. If the ball icon is next to it, that means that you've caught that Pokemon. Now this is stored in Pokedex order. It's stored in memory as a bitmap. When you encounter a Missingno, it tries to mark that you've encountered the hypothetical 256th Pokemon. But remember, there were only 151, so it actually writes past the space used for this, which happens to be, you get it. So immediately after your Pokedex data in RAM is your inventory. So it ends up setting the high bit of the 13th byte after the end of your Pokedex. So the inventory is stored as 1 byte and then followed by 1 byte for the item's ID and then 1 byte for its quantity. So it ends up meaning that it sets the high bit of the 6th item in your inventory. To put it a different way, as long as you had less than 128 items, it will add 128 to your item's quantity. So this bug would have been avoided if there was some kind of bounds checking in sprite decompression. But everything in this game was optimized for code size. And if you're only dealing with a known set of trusted inputs, omitting that seems perfectly reasonable. The only reason the code misbehaved was because of an unrelated bug causing the sprite decompression algorithm to get garbage data. And Missingno was safe to catch because aside from its sprite, all of its other data was valid data. It was just zeroed out. So this is what it looks like when you send out Missingno, if you've caught it. So now that we've seen every piece of this glitch, we can see that it was really just a bunch of small, seemingly benign interactions between unrelated bits of code. No individual piece of this glitch stands out to me as something that's obviously wrong or something that would have been stopped in code review. When you combine all of these together, you get one of the most famous glitches of all time in any game. But it's not the result of some horrendously bad coding or a lack of QA. Every piece of this glitch was relatively benign or due to completely unrelated parts of the code base interacting in unexpected ways. This was handwritten in assembly under massive space constraints. Every instruction mattered. I don't think that I really would have done better than they did, and I doubt anybody would have done much better than they did. A phrase I've heard from folks who make fun of the game are oh, it was just completely broken. The whole game was just so buggy. And I think we should probably just stop saying that about things like this. In this case and in many other cases, it's likely the software was developed under some constraints that we're not aware of. And we likely wouldn't do better in the same circumstances. I'm really glad that we don't have to like hand roll assembly anymore. A lot of this glitch boils down to because it was assembly. It's easy for us to take for granted the technologies we have at our disposal today. Today, code size is rarely a hard constraint. We run our code on machines powerful enough to include all sorts of like safety checks and things like this just wouldn't happen. But in 1996, just use Ruby, just use Rust wasn't an option. Even using C wasn't an option on the Game Boy. There's actually a really high quality disassembly of the game, which my wife and I, Sage, used to prepare for this talk. It doesn't have the comments that the real source code had, but it was really invaluable and it's open source. So I want to thank them for that. Thanks to the organizers of Rocky Mountain Ruby for having me. And thank you to my wife, Sage, who's not here today, but we co-wrote this talk together. And thank you, everybody.